So, good morning, everybody. My name is Paulo Selegim Jr. I'm from the University of São Paulo in Brazil. And it's a great pleasure and also a great honor to be here to be able to talk about the projects I'm conducting in Brazil related to bioenergy. And the subject of my talk today will be the development of an integrated agro-industrial model for the sustainable production and conversion of biomass into biofuels and added value products. But first, I would like to talk a little bit about the way humankind uses energy. We need energy basically for two things: to sustain our life processes and also to support our lifestyle. Regarding our life processes, we can calculate a number by taking the amount of energy contained in the food that we ingest every day, around 2,500 calories a day. If we convert that to watts, we get an average power of around 120 watts. This power varies between 90 watts, which corresponds, for instance, a guy sleeping on a couch, and we may have also very high and short peaks of power, like 2,000 watts, which corresponds to a very intense effort, a professional athlete, for instance. Regarding our lifestyle, the support of lifestyle, we can calculate an average power by taking the amount of energy produced all over the world, around 500 exajoules per year. If we divide that by 7 billion people, which is more or less the population of Earth, and convert years to second, we get this average power, 2,300 watts, which is spread in industrial and agricultural activities. The share corresponds today to 28%, and this share tends to be kept constant in time. This power supports the transportation sector. The share today is 27%, and it tends to increase in time, especially because of the developing countries becoming more demanding in terms of transportation of goods and people. Also, this average power serves residences and the services sector. The share today is 36%, and it tends to decrease, especially because of the incorporation of new technologies into the residences engineering, like more efficient illumination systems, more efficient insulation systems, more efficient air conditioning and heating, and so on. But the point here is the huge contrast between the power that we need for our metabolism, in fact, and the power that we need to sustain our lifestyle. So the point here is that energy is closely related to quality of life. We can assess this by plotting the Human Development Index in terms of the power per capita per year. And we see that between 0 and 3 kilowatts per person, there is a clear trend between quality of life and the amount of energy that everyone has for himself. This energy actually is for transportation, for the food that we have access, for medicine, for everything actually. Beyond 3 kilowatts, there is a strong influence of the petroleum-producing countries like Norway, for instance, which is the highest HDI, and the Emirates, which produces a lot of energy, but the quality of life is not as high as in Norway or United States and Canada, for instance. But we can see this limiting number here, 3 kilowatts per person, as a target. And we can make a simple calculation. For instance, let's consider the developing countries, China, India, Indonesia, and Brazil, and we can correct the corresponding HDIs to 0.9, which is a fairly good quality of life. Just by doing that, by correcting the HDI of China, India, Indonesia, and Brazil, it is simple to calculate that there will be a 41% increase in the world energy consumption just by increasing the quality of life in these countries. So we see that energy actually is a very important bottleneck for increasing the quality of life all over the world. And bioenergies will play an important role in meeting these expectations, that is, increasing the quality of life of everybody. But how renewable energies will displace fossil energies? This is another very important question. And the point is that modern bioenergy constitute a disruptive technology. Let me elaborate a little bit on this. What is disruptive technology? We can take an example, the problem of digital storage media. We can assess its performance by several parameters. For instance, the storage capacities, dimensions, frequency band, and so on. And also, it is interesting to assess its robustness, durability, cost, interchangeability, and so on, and plot this in function of the time. We started with the paper punch cards, then we migrated to the magnetic tapes, and with the introduction of the floppy disks, I don't know if you remember that, but with the introductions of the floppy disk, the access to the digital data that was stored in this media increased a lot, because to assess a data that it was inside the band here, you would have to rewind or fast forward the tape, so it takes a lot of time. In the floppy disk, you just move the magnetic head here to the correct place. So there is a strong leap in the performance of this new technology. The old technology still continues to exist for some time, and then eventually it disappears. With the introduction, after a few time, of the CDs, the floppy disks were eventually abandoned. Also, they remained for some time, but they are now disappearing. Regarding the robustness, every time you have a new technology being introduced, it is natural that you have a drop in robustness. Why? Because this new technology has not been yet subjected to testing, to experimentation, to refinement, and so on. So, for instance, not everybody, when the CDs were introduced, not every PC had CD lectors. So it's not as widespread as were the discs. So the robustness decreases. But you need some time. You need some evolutive optimization of the new technology in order to increase its robustness. Our point in saying this is that energy follows the same pattern. For instance, let's take the problem of fuel for autocycle engines. We grew up in the gasoline era, okay? And we are now changing to first generation bioethanol, especially in the United States and in Brazil. With the introduction of the first generation ethanol, the robustness dropped, as for instance, you couldn't be really sure that you would find ethanol in a gas station, so it was less sure, technology that was less sure. And also an important point is that with new CO2 sequestration technologies, probably gasoline will continue to exist for a longer time than it would be natural. We also have the second generation ethanol, which by replacing first generation ethanol solves some problems. For instance, the influence of first generation bioethanol in the price of food. This is a problem of the robustness of this new technology. But with a second generation bioethanol, this could be solved. But it's still a much more expensive technology, and it's still not scalable technology. So it is, this picture here is what we expect for transportation fuel. So, in conclusion, second generation ethanol is a very promising energy vector because it can be produced from lignocellulosic fibers, because there are abundant feedstocks, crops and wastes, and also it can virtually coexist without impacting on food prices. It is also a strategic importance for Brazil, especially because of the sugarcane sector. We already have an oversupply of electricity from biomass residues in São Paulo, from biomass sugarcane bagasse, for instance. We need automotive fuel more and more because of the development of the Brazilian economy, and also because the sugarcane sector is already a mature sector in Brazil.